All right, so the topic of this lecture will be randomness and chaos. And so these are two terms that are often mixed in popular language, but more formally, from a dynamical systems point of view, these are very, very different terms, and they are almost even opposites. And so in this lecture, we're going to sort of talk about the two of these with the background of what we've learned throughout the semester about this particular type of dynamical systems modeling. But I'm going to break the lecture up into sort of small parts. And so I'm going to focus primarily on randomness in this lecture. So randomness is a modeling tool that simplifies model building, whereas chaos is an apparent randomness that emerges from a system, a model, or even a real system that is fundamentally not random. So randomness is actually something which makes our modeling easier, and chaos is something which in some ways it makes modeling harder, but also makes sort of using models harder. And we will get into sort of chaos in the other parts of the lectures, other videos of this lecture split out. But this particular part is I'm sort of focusing on randomness. So when we talk about using randomness in models, we move into the area of something called stochastic modeling. And so this term stochastic, when we use it, we're generally referring to the use of building models that use randomness instead of deterministic rules. And so the term stochastic, it's actually originally a Greek term which represents guessing or conjecturing. And so it's sort of, seems maybe strange today to associate it with randomness, but the basic idea is that when people started using this term, there was a big push for models which captured all of the fine-grained deterministic details of real systems. But there was a realization that if we just made the conjecture that even if the underlying processes were deterministic, and very complicated, we could maybe forget about them and assume instead that they were fundamentally random. And if we did so, then maybe we wouldn't have to build so many things into our model. And maybe we wouldn't need to get all of the connections among those things quite right. We could kind of filter over those by just using a random behavior instead. And so we're not saying that the real system is actually fundamentally random, but we're saying that we're going to have a better chance at modeling it computationally or mathematically if we assume it's random instead of what it actually is. And so that's why stochastic comes from this idea of conjecturing. So if we go back to some earlier examples in the class, I talked about modeling bacterial growth, bacterial reproduction, and bacterial death. And so focus here on reproduction. We talked about how in real life you'll have one bacteria for a while, and then after some average time, we'll call it W, then you'll get two bacteria. And so there'd be a reproduction event which actually created these two bacteria out of one. So you'd start with this one bacteria, maybe you get a reproduction event, and then you wait a certain amount of time, and this might be less than the average time W, and you'll get another reproduction event, and then you wait another amount of time, and that also might be less than the average time, and you'll get another reproduction event. But then the next time you wait, it might be more. So you get some of these inter-arrival times or inter-reproduction times being less than the average time and some being more. And so what we did when we needed to build these system dynamic models, which are fundamentally ordinary differential equations, but we've been simulating in VinSim or InsightMaker, numerically integrating them, we sort of took this kind of compound interest conceptual framework where we said, well, rather than them being these discrete events that occur that produce exactly two bacteria, what if we say instead, if we know that on average we go from one bacteria to two bacteria every W time units, then maybe every one bacteria can be modeled as just continuously pouring out 1 over W bacteria. And if we have some sort of time step we can sort of say that during that time step, we can calculate how much new bacteria poured out. And then in the next time unit, we can add this fractional bacteria to our bacterial pool, much in the same way that if you deposit money in a bank and you let that money sit there in the bank, then the bank will give you interest, but only after some compounding period. And so there's some compounding period where you get a fraction of your money back in interest, and then it gets added to the pool, and then that then starts accruing interest on itself. And so this idea here is sort of summarized in this cartoon where we start with one bacteria. It's going to give us this fractional unit here. So this is our bank balance, the bacteria. This is our generated interest. We've been calling the amount of bacteria a stock, and we call the amount that is being contributed from each bacteria a flow. And the interest is that flow rate times the time interval. So in the next time step, or the next compounding period, we take the original principal and the interest, and that becomes all principal, and then both of them start pouring out their own interest, and then that repeats. And that kind of ends up being the perspective of how the average number of bacteria change over time. So if you're looking at that petri dish from afar and you look down at it, you see these nice spheres or these nice circles that grow at what looks like a smooth rate. And that, from the mile-high perspective looking down, then we're sort of capturing the average behavior, and that seems to be kind of good enough. And so we're saying from this perspective, we're saying that if we know what the average population is at one time step, we're assuming that we can predict perfectly what the average behavior or average population will be at the next time step. So we are, okay with needing these sort of perfect predictions in our deterministic model, because we're not saying we're modeling the actual populations. We're saying we're modeling the average of those populations. But imagine if we actually want to do more than just modeling the average. We actually want to model the realistic variability around the average. So we want to see, sometimes do I get faster growth? Sometimes do I get slower growth? And so on and so forth. So if I wanted to do that in kind of a deterministic, all-inclusive, endogenous framework, then I would need a process that would actually produce each one of these little less than W and more than W time delays. And so I'd have to ask, well, how do I sometimes get a less than W time delay and sometimes get a more than W time delay? Well, I might need to know things about the internal physiology of the bacteria. I might need to know that some bacteria are hungry in the petri dish and the other ones aren't as hungry. Some have more nutrient availability, the other ones don't. Some might be sitting in a warmer part of the petri dish, the other ones aren't. I might need to know the age of each bacteria. There's all of these different things that will end up that I'll end up needing to know in order to produce variability that looks like the variability that I have in a real population. In other words, I almost have to build a synthetic bacterium from scratch in order to get the same variability out. And I might not even know all of the details that go into a single bacterium, so I may not be able to do that. And even if I could model that, it's going to be a very, very complicated model with a lot more there. And it doesn't seem like it would be worth it just to get, a realistic prediction here, because I'm probably going to be way off when I start making these assumptions about how these synthetic bacteria work. So it's very costly to try to make a deterministic model that has this sort of variability. So we say, well, in a stochastic modeling approach, if I look back at these bacterial growth and I look back at these times, I say, you know what? What if I just assumed that these times were determined randomly? I know that behind the scenes there's probably some very precise deterministic physiological process which allows me to sort of predict that this bacteria will reproduce quicker than, say, this bacteria. But what if I just rolled a die and I say got a 6 here, and I'd said, well, I'm going to multiply whatever number I get here by 10 seconds. So then this becomes 60 seconds. Then over here I got a 2, so this becomes 20 seconds. And over here this is another 6, so this becomes 60 seconds. What if I just generate these times by rolling these die over and over again? Would I get something that looks much different? If I get the kind of right die that kind of comes up so that it's maybe bacteria tend to reproduce, maybe there's only a few that reproduce at very short time intervals, and most of them are longer time intervals. So I might not need a fair die, but if I sort of got a die that would have the right weight, the right balance of outcomes, then maybe I could get something that looked pretty much like a normal bacterium. And as long as the average waiting time between reproduction events was right, then maybe I would have a very plausible looking outcome. Well, it turns out that if I take, say, a 20-sided die like the one you see over here, and then I just create a mapping to sort of simulate a 6-sided die like the one over here, I can actually get whatever biased distribution I want, even though I maybe started out with an unbiased distribution. So this is kind of one of the interesting tools of stochastic modeling, is that if you have a uniform distribution, so in this case this 20-sided die gives me an equal probability of getting any of those 20 outcomes, then I can create a mapping where I can say, well, if I get a 1 through 10 from the 20-sided die, then just pretend like I got a 1 out of a 6-sided die. Otherwise, if I get 11 or 12, give me a 2 out of the 6-sided die, 13, 14, 3, and so on. So basically what I'm saying here is that half of the time I'll roll a 1 on my simulated 6-sided die, and the other 50% of the time will be divided up, where 10% it's 2, 10% it's 3, 10% it's 4, 10% it's 5, and 10% it's 6. So I can actually, so now my modeling task goes from modeling the details of what goes on inside a bacteria to describing statistically how often different reproduction events actually happen with real bacteria, and then setting up one of these maps so that if I'm rolling a 20-sided die, the die that I end up simulating with one of these maps ends up being matching the kind of times that I get out of the bacteria. And I could even make this kind of simpler, is if I just want to know two things, like we're going to see in a second, did the bacteria survive or not? Then the mapping is even simpler, where I can just sort of say, well, if I get any number 15 or below, I'm going to assume that I flipped a heads in an unfair coin. And then if I get 16, 17, 18, 19, or 20, I get a tails. And this will give me a coin that comes up heads 15 out of 20 times. And tails only 5 out of 20 times. So it's so that's 25% of the time it's tails, 75% of the time it's heads. Hope I did that right. I hate to do math on the spot, but so that shows here that as long as I have a source of uniform distribution of numbers, then I can generate whatever random distribution I want. So as long as I have a random distribution I'm shooting for from reality, I don't care how that random distribution actually cropped up in the underlying process, just so long as I can approximate it, then maybe I can do just as well as if I had a deterministic model, but it's a much, much simpler model. Now, inside a computer, you don't have a source of randomness, at least not a good one. Not a normal computer does not have a true source of randomness, and the sources of randomness that are built into normal computers are a little bit limited in what you can do with them. And so instead, what computer simulation designers have done is they have given us streams. So these you can think of as sort of sequences of known random numbers that are stored inside the computer. In reality, they're actually mathematical functions that if you give them the previous outcome and you put that back into the function, it will give you a new outcome, and all of the string of outcomes you get end up looking like a reasonable approximation for rolling a die or a similar sort of random event. But if you were to sort of start that sequence over again right at the beginning, you would get the exact same string out again. So that would be pretty weird if you grabbed a 20-sided die and you rolled it a bunch of times, and then you put it away, and then the next day you got it out again and rolled it, and you got the exact same sequence out again. Well, that's very much the way randomization works inside a computer. So instead, the simulation designers have designed for us multiple streams. And so if we really want different outcomes, like we want to say, well, let's see how the bacteria might grow on one day, and then let's see how the bacteria might grow on another day, we can set up the same stochastic model, but we can tell one model to use stream 0, another model to use stream 1, and so on, and then we'll end up getting the variability that we might expect in a real population. So for two simulations to have different outcomes, you have to use different streams. But otherwise, we can consider those two simulations to sort of be random, even though that fundamentally they're being generated by things that are only approximately random. All right, so let's see what the outcomes of this, or what the consequences of all this are. So I'm going back to a simple deterministic model of population growth that we see right here on the screen. So there's a deterministic population. It's just a stock. It has an outflow here. So I have a flow that I'm calling deterministic deaths, and I've got the average lifetime in here. So take a minute and think about this. What formula do you think I should put in this flow here? To the more mathematically inclined of you, if you call this x, you can think of this as minus dx dt. And if I think of this as a population where each individual has an average lifetime here, then I'm asking for sort of what do you put in for this dx dt, or this minus dx dt formula. So the formula we're looking for here is just going to take for every member of the population, they have a contribution to the outflow of 1 divided by the average lifetime. And so the total outflow for the total population is just the current population divided by the average lifetime. And so that's the formula that we'll use there. And if we simulate, we get this nice smooth exponential decay. Starts with an initial population of 1,000, and then it smoothly decays down to eventually gets close to 0, but it'll never actually quite hit 0. So, and this is a representation of the average behavior of a bunch of petri dishes as they sit there and die off over time. Now, this doesn't capture any of the real variability. Like I said, this smooth decay isn't ever actually going to hit 0. It's only going to get closer and closer and closer to it. It's going to have fractional bacteria, so it's not actual counts of bacteria. It's average numbers of bacteria. And so some petri dishes are going to be lucky and they'll actually hang on for longer. Some are going to be unlucky and not hang on so long. And then some will be pretty close to this trend here. But there's going to be variability in the real population. So how do we generate simulation outcomes that look more like a real population? Well, now we're going to move to this stochastic model, where now our stock, I'm calling a stochastic population. And I have this thing, this outflow, I'm still calling it a flow, called stochastic deaths. Now in this class, we use VinSim and InsightMaker in order to do our dynamical simulations. VinSim and InsightMaker really aren't built for this type of stochastic modeling, and so we have to kind of figure out a way to turn these discrete events into flows that can be simulated by these tools. And that's why it's going to look a little funny and maybe not as straightforward. But that's the reason why this deaths flow actually takes the time step, the dt, actually as an input. And it also takes random stream as an input. So this could be a number, 0, 1, 2, 3. This is saying inside the computer, do I want the sequence index with 0, with 1, and so on. And then our average lifetime comes in as before. So the idea here is I start with a certain count of bacteria, and what I want to do is to say which of these bacteria will survive to the next time step of time. And so the way I'm modeling that is by flipping a weighted coin, so an unfair coin for each bacterium. And so the idea is that the probability that the coins will come up heads is the probability that a bacteria will die in the time step. And if I choose a small enough time step, it's got to be much, much smaller than average lifetime, then it turns out that you can approximate the probability that any bacteria will die, any single bacteria will die in that time step as just time step divided by average lifetime. So that gives me a probability. And I can say, well, imagine I flipped the coin 1, 2, 3, 4, 5, 6, 7, 8, 9 times. How many of those 9 times came up heads? And I'm representing those by these thumbs down, as in these bacteria were the ones that were that died off. It's like playing Russian roulette with bacteria. And so the red ones are when the bullet got fired, and the purple ones or the magenta ones here are when the bacteria got lucky. So we then subtract out these bacteria that were selected to be removed from the population, and all we're left with is a smaller population. But we're left with a full population, so it produces a whole number of bacteria. There's no fractional bacteria anymore. So how do we implement this inside a program like VinSim or InsightMaker? So I'm focusing on VinSim here, but the solution is similar to InsightMaker. So there is this function inside VinSim called random binomial, it's sort of a funny name, but if you remember from a probabilistic course, you maybe think about these Bernoulli trials and the binomial distribution, and that's where this kind of comes from. If you don't remember any of that, that's fine. But basically, random binomial is a way in which the VinSim will give us a random outcome, which represents how many tosses of a coin come up heads, given that you tossed them a certain number of times. And so we put in a random stream into this VinSim function here, and from that random stream, it will then give us these random outcomes. So let's see what each one of these parameters are. So the first thing is we have to divide this random binomial by time step. This is one of the weird things that we have to do to get a system dynamics modeling tool like VinSim to act like a discrete event system simulation tool. And so we're basically saying that random binomial is a count of events that occurs during a time step. And if we divide that count by time step, that turns the thing into a flow. And we need things to be a flow or a rate in order to be able to be put into VinSim. So that's why we've got this weird divided by time step here. So then if we move on, then there's this random stream, and I already mentioned that that's where you would put a number like 0, 1, 2, and that tells VinSim which sequence of random numbers it should use when it's throwing its effectively like its 20-sided die, or its equivalent to a 20-sided die, or even an infinite-sided die, in order to generate these random binomial outcomes. And then there's these parameters 0 and 1, which are known as the shift and stretch, and all of the VinSim random functions have these. These are a little more advanced, so I'm not going to spend much time on them. For these cases, we're pretty much going to leave them always at 0 and 1, but if you get into more advanced modeling of these distributions, then this allows you to generate shapes of distributions that may make more sense for your system. But for our purpose, for modeling this particular death process here, this is fine for us. I'm just leaving them at 0 and 1. Then the number of tosses. So the number of times you toss that coin to see if it comes up heads or tails. In our case, each bacterium left in the population is a toss. And so that will end up being stochastic population. The probability of a single coin toss coming up heads shows up here, which in our case will just be the time step divided by the average lifetime, because that gives us the probability of death in a single time step. And then finally, this min and max over here, these also are a little more advanced parameters. They allow you to draw from a distribution like this one, which will give you a number greater than 0, and they allow you to sort of toss out possible outcomes that are outside of a particular range. We don't need to do that. We want the full sort of binomial here, so we're going to set 0 to the minimum and the number of tosses to the maximum, so we don't worry about that. So we bring everything together, and here's what we end up getting for our stochastic deaths formula. So again, there's 0, that's the min, there's stochastic population, that's the max, but the really important line is this middle portion here, where we've got our probability of a death of any individual bacteria in a time step. And then we've got the number of tosses, the number of bacterium we're sort of trying the Russian roulette out on. The 0 and 1, that's the shift and stretch that we don't worry about. We just leave them as 0 and 1, and then our random stream in there. And so if we do that, and then we hit play or hit run, we end up getting a result that looks like this one. So I've got in blue, the thick blue line, that's our old result from the deterministic formula up here. And then this little red line that you can kind of see diverting from the blue and then coming back and touching it and then coming up around over top of the blue and then coming back and touching it, that is from our stochastic simulation. And so you can already see it varies a little bit. And if I can zoom in on a particular portion there, and I see now that, yes, it does deviate from the average here. And you can see it sort of holds a steady value until some time in the future where then it jumps down by 1 and then holds that value and then jumps down by 1. And the time in between each jump seems to be variable. So that is what we want. We wanted variable times in between these jumps. So now bacteria aren't sort of continuously dying like they are in the average here. Then they are decreasing so that you always have a whole number of bacteria, and some bacteria live longer than others. And so that's, like I said, just what we want. Now, what happens if I go into this and I try using different streams? So that previous one was showing you with something with stream 0. Well, if I set stream 1, 2, and 3, then I get these 4. My original stream 0, which is the red line, and then I've got 1, 2, and 3, which are the green, gray, and black lines. And you can see I get, they all hug the kind of blue average behavior, but I get a lot more variability here. So this gives me a much better impression of what sort of variability I might expect in my population. So I can zoom in on that, and here you see that variability there. So this kind of helps us confirm that our deterministic model does appear to sort of match the average behavior. If all we cared about was the average behavior, it would have been much better for us to use our just deterministic model, because we can run one simulation that actually runs a lot faster than the stochastic one, and we end up getting that average behavior out. Here, I had to run 4 simulations, and in reality, really to sort of fix this average behavior, I probably should run even more simulations so I can get a better spread of outputs and then sort of average them all up, and then that would sort of help give me this average behavior coming down here. So if I really just care about the average behavior, then I should just model the average behavior. The only time I would then flip to the sort of stochastic behavior is to capture this variability. So that's sort of, in a nutshell, what stochastic modeling is all about. They allow for us to capture, or stochastic simulation, I should say in particular, allows us to more fully capture realistic variability in our simulation studies. And there's the upside to that. Maybe I'll get rid of myself here for this summary piece. So the upside of that is that the simulations are much more realistic. We have, discrete counts of bacteria as opposed to fractional bacteria. Some bacteria live for longer than others. It adds to that realism. But the downside is that it is a little more computationally costly. So we have to do more simulations needed in order to understand general trends. So this kind of, we've been talking about the kind of modeling continuum, how you've got like an analog side, which is like you're actually modeling something that's almost exactly the real system. Maybe you're experimenting out in a fraction of the real world. And then you've got the sort of more metaphorical side of the modeling continuum, where you've got something that looks a little more maybe mathematical and so on. And so there are pros and cons. We might get more generalizable insight from the blue line here from a deterministic model, but we lose the variability. As we go to the variability, we get more realism, but it ends up being more difficult to generalize and more difficult to actually run the simulation. So there are pros and cons. I can't say one is always better than the other, but if you need more realism, going towards the stochastic model is one way to get there, and it doesn't require you to build an actual model of all of the internals of a bacteria. And that's kind of the big point about this stochastic modeling, going back to the conjecture that we're going to assume that fundamentally our phenomena are random, even if they aren't actually. Okay, so that's the main point, but I did want to give one more tip, at least with respect to VinSim, and again, there's an Insight Maker side of this as well. So in the particular example I gave, where we use that random binomial, that really is only an appropriate technique to use if you are, if you know that the probability of this event doesn't vary with, say, the number of the bacteria in the population. So we know every bacteria has the same probability of dying in the time step, regardless of how many bacteria are there. Now, the probabilities can be state dependent as well, as in sort of infections in an SIR model or something like that. And in those cases, we kind of can't, we don't have the luxury of being able to make a large time step and ask how many, possibly many events happened in that large time step. So what would we do instead? Well, in VinSim and also in Insight Maker, there is another random distribution and another way you can use it that allows you to turn any flow rate that we've built in our system dynamics models and our stock and flow models into a stochastic realization, or into a stochastic implementation, I should say, in the stochastic modeling. And it looks like this thing down here. So you can use this if then else, and this thing called a random uniform. Now, the random uniform is like an infinite-sided die. It will give you a random number, a random real number in between 0 and 1. And that random real number you can sort of compare to a probability. So if you remember in our 20-sided die, I said if we get an outcome of 15 or less, then we're going to say that we got a heads. And if we get an outcome of 16 or higher, it'll be a tails. And that will end up making it so that our coin will turn up heads 75% of the time. Well, you're doing the same thing here, where you end up getting from this random uniform 0, 1, an outcome that is between 0 and 1, and it kind of spreads the probability out evenly over that interval. And so if you compare it to a probability itself, then this then the number that gets drawn will be less than the probability, with exactly the probability of the probability here. So if you wanted 75% here, you put 0.75, and then if you draw a random number between 0 and 1, if it's uniformly distributed between 0 and 1, it will be less than 0.75 exactly 75% of the time. So it's a convenient tool if we have a flow rate and we have a very, very tiny time step, because those flow rates, if they multiply it by a very, very, very tiny time step, turn into probabilities that an event will happen during that time step, a single event. But you really have to make the time step so small that there is no probability that you get 2 or more events happening in that time step. So if you can manage to squeeze that time step down to that level, then you can use this basic formula to turn your system dynamics model into a stochastic simulation that has that variability. And you can even then use different random streams, and putting a 0 here, a 1 here, a 2 here, etc. Will end up giving you different realizations, different outputs every time you run this simulation. So that's the general trick if you want to start using this in VinSim or Insight Maker to generating stochastic simulations or discrete event system simulations. But like I said, VinSim and Insight Maker are really sort of built for system dynamics models, this kind of smoother modeling, and this is kind of just a shoehorned way to fit that into that. If you're really interested in this so-called discrete event system simulation, there are a lot of other packages, and there's actually even entire courses just on that type of simulation. All right, so that's the end of this segment of the lecture. The next segment of the lecture is going to be contrasting randomness with chaos, which is a very, very different phenomenon. So I will see you for that one.